Hello everyone, my name is Duygu İçen and I'm from Hacettepe University Department of Statistics. Today I'm going to give you a talk about big data concept for statisticians. In the public discussion which takes place in any sector, moral, political, social or scientific, themes encapsulated by keywords often arise. Those keywords may not always be particularly well defined, but they become part of the common discourse. In the scientific area, big data is a good example. As an expression of the size and complexity of the data sets, which now arise routinely, and the challenging issues of analysis and interpretation, which have to be confronted, the term is quite a useful one. Unfortunately, the expression of big data is often used in a manner which implies that solutions to these issues are readily available. A variety of other terms have become associated with big data, including machine learning, artificial intelligence, data analytics, and data science. Criticisms are sometimes leveled that statistical thinking hasn't adapted to the new challenges and that these new modes of thinking are required to make progress. While it has to be recognized that much, more powerful and sophisticated computational methods are now required. Closer inspection reveals that statistical methods remain as a fundamental component of all these areas. If the aim is excellent science in the sense of understanding how processes operate, then statistical models provide enormously powerful tools for any situation where measurements exhibit variability. They enable us to draw clear conclusions and give clear expressions of uncertainty. While other forms of computational expertise are also required, the central place of statistical thinking remains unchallenged. As a unique combination of the scientific reasoning, probability theory and mathematics, statistics is a necessary component for the big data revolution to reach full potential. This talk is about introducing some problems in large data and what the big data means by the eyes of a statistician. Theory tells us that in principle having more data is always good. With new data comes the potential for more information, and if this were not the case, one could always discard that data. No harm could possibly come from having more data. The flaw in this reasoning is that in practice we do not discard data but try to look for patterns therein. A tempting pitfall is to torture the data until it appears to support some preconceived idea. This is not to say that data analysis shouldn't be driven by pre-specified hypotheses, but then an adequate strategy is required to reduce the chances of non-reproducible findings. The last 2 decades have seen exciting advances in statistical methods to disintegrate signal from noise in massive data. But these advances have not yet reached routine analysis. Hence, I will try to look at big data as statisticians. We are entering the area of big data, a term that refers to the explosion of variable information. Such a big data movement is driven by the fact that massive amounts of very high-dimensional or unstructured data are continuously produced and stored with much cheaper cost than they used to be. This is also true in other areas such as social media analysis, biomedical imaging, high-frequency finance, analysis of surveillance videos, and retail sales. The existing trend that data can be produced and stored more massively and cheaply is likely to maintain or even accelerate in the future. This trend will have deep impact on science, engineering, and business. For example, scientific advances are becoming more and more data-driven, and researchers will more and more think of themselves as consumers of data. The massive amounts of high-dimensional data bring both opportunities and new challenges to the data analysis. Valid statistical analysis for big data is becoming increasingly important. As everybody knows, the definition of big data firstly comes into scientific life as 3 V's of big data: volume, variety, and velocity. In the following years, this definition was followed by 4 whys and 5 whys of big data, as you see on the slide. We are in a time that big data is mentioned with 10 whys of big data. This is a small graph represents the progressive of whys for big data in a time. There was only 3 why when the big data started to be talked about for the first time in the scientific world in 2001. Then they grow a little big and the terms value, veracity and variability are added to them. In 2014, more whys of big data were introduced and accepted in the scientific world. Now I want to ask you something. How many whys of big data could have been talking at scientific world according to you nowadays? Can you guess a number? Okay. Nowadays, the 42 whys of big data has been talking about. According to Schaeffer, this number is expected to increase further. So why? According to Google, we see that what happened on the internet at every 1 minute. Let's look inside some of them. More than 156 million emails are sent, and more than 3.8 million researches are made on Google. More than 800,000 files are uploaded on Dropbox. You see the values of other numbers. In this great rain of data, we have to continue to say that what we have said for years as statisticians. Trust me, I'm a statistician. We need to give a correct and consistent answer to all these questions for people to trust us while analyzing big data. When, where, and why. Shortly, when, where, and why should people trust us while analyzing big data? Okay, but why would they trust us when we are exposed to this huge stack of data? Because now data scientists began to be more preferable than statisticians. When it comes to big data, the data scientist, computer engineer, and statisticians are focusing on the same points and analyses. As the time progresses, it is expected that these jobs will be closer and more integrated than now. Therefore, when working with large data, we need to highlight the quality and leadership of statisticians. I think this is possible with the answer to the 3 questions you see on the slide. 3 W's for statisticians in the area of big data. I'm a statistician, but does that mean I cannot be a data scientist or a data analyst and claim expertise and knowledge that are highly relevant in this area of big data? Does a data scientist have different skills? Should I feel threatened professionally, and is my discipline becoming irrelevant? We are all part of the information ecosystem, as Gore said in 2017. We have moved from systems of rather clunky data acquisition, taking days, weeks, months, to now the Internet of Things, social media and the citizen scientists, with data arriving at unprecedented rates, where everyone may have access but may not have the skills needed to make sense of data. Who checks the quality? Who understands bias and lack of representativity? Who appreciates the variability? Statisticians. Others in many disciplines write about the data leak, and organizations sometimes describe themselves as data-rich, information poor. Increasingly, there is a discussion about the data and digital economies. Who is well placed to swim and not shrink in this ocean? Statisticians. Statisticians are supposed to be one key player in the area of big data because statisticians work on data analysis all the time. However, computer science has made such great progress in big data analysis, and statistics are left behind. Computer science is running like an energetic kid, and statisticians are moving slowly like an old man. Now it's time to fill the statistics with running, jumping, and leaping energy. The database community is aware of the need of managing big data since its infancy. Turning Edward invented relational database in the early 70s. The Very Large Databases Conference, which is the most prestigious in the field, started in 1975. Since the mid-18th, companies such as Oracle, IBM, and Microsoft built a substantial portion of their commercial success thanks to data management software. Data management initially applied to the financial world and then extended to all commercial activities. More recently, search methods over big data are key to the success of Google and Yahoo, while data analysis methods such as association rules are key to the success of Amazon. In the new century, social networks such as Facebook, LinkedIn, Twitter, and Instagram are large data collections associated to a business model which emphasize data sharing. Similarly, the so-called sharing economy is based on social use of big data. The emphasis on big data in computer science and statistics is described in the fourth paradigm book in 2009. In the preference, the history of science is historically separated into four phases. The first based upon empirical science and observations. The second upon theoretical science and mathematically driven insights. The third upon computational science and simulation-driven insights. The fourth upon data-driven insights of modern scientific research. Accordingly, we have entered the fourth phase, featuring the data-driven approach. In the data-driven approach, computer scientists are playing the leading roles. However, there is a discussion about two cultures occurs in the scientific communities of computer science and statistics. According to model-driven approach, models are built in the mind of scientists, then they are formally expressed, and they can be tested, experiments confirm or falsify them. In statistical terms, data are generated by a stochastic model, which must be understood. According to Bryman, in the past, the statistical community has committed to the almost exclusive use of data models. With the advent of big data, however, the classical approach to science hypothesis model test has been put in question, and a data-driven approach is emerging, which consists of being driven by data rather than by prior assumptions. An extreme point of view is that we can stop looking for models. We can analyze the data without hypotheses about what it might show. We can throw the numbers into the biggest computing clusters the world has ever seen and let statistical algorithms find patterns where science cannot. We have to admit that it's difficult to keep up. How can you expect someone who is trained in dealing with data sets of n is equal to 30 observations with 3 variables to suddenly cope with a 100,000 increase of n is equal to 3 million observations and 300,000 variables, for example, or even worse? Everything has to change. Summarizing a dataset becomes a major computational challenge, and p-values take role where everything is significant. Yet, dealing with a wide range of sizes of datasets has become vital for the modern statistician. We need to make sense of the huge, rich seams of data being produced underlines the great importance of statistics, mathematical and computational sciences in today's society. But what is new about data? Data has been used for centuries. All of these small datasets are at the core of important issues for mankind. So it is not the data or its importance, but the size, structure, and ubiquity of data that is new. Many of the challenges in the new world of statistics in the age of big data are of a different nature from traditional scenarios. Statisticians are used to dealing with bias and uncertainty, but how can this be handled when data sets are so large and collected in the field without traditional sampling protocols? What do you do with all the data is an important question. The last 20 years has seen an explosion of statistical methodology to handle large P. Often with sparsity assumptions, large N used to be the realm of careful asymptotic theory or thought experiments. But in reality, one often does encounter large N now in practice. To handle the challenges of big data, we need new statistical thinking and computational methods. For example, Many traditional methods that perform well for moderate sample size do not scale to massive data. Similarly, many statistical methods that perform well for low-dimensional data are facing significant challenges in analyzing high-dimensional data. To design effective statistical procedures for exploring and predicting big data, we need to address big data problems such as heterogeneity, noise accumulation, spurious correlation, and incidental endogeneity, in addition to balancing the statistical accuracy and computational efficiency. For any finite parametric model, confidence intervals become extremely narrow and p-values become very small indeed. Bayesians fare little better as the prior is swamped and the likelihood dominates with similar all-too-sharp inferences. One can use non-parametric inferences to grow the parameter space at a sensible rate to avoid some of these problems. But even with this, the inference becomes far more certain than common sense would allow. Machine learners have tended to avoid the problem by not providing estimates of uncertainty. Uncertainty comes from other sources than unknown parameters. We are not sure what model to use and we are uncertain about the biases and errors in the data. If we were better able to incorporate these in our modeling, we would achieve a more realistic results, but this is difficult to achieve. Small data models are necessarily simple and reflect at least some uncertainty. We know about the dangers of model misspecification. Although the results may not calibrate the uncertainty perfectly, at least the user of the conclusions will understand that they should be cautious and allow for the possibility that they are wrong. In contrast, models for high data might be fine for point prediction and classification, but we struggle to provide realistic assessments of uncertainty. Also, consider the problem that big data suggests a massive number of hypotheses with less protection against the danger of false positive rules. In the time, we may learn how to express uncertainty realistically in big data inferences. But for now, we might prefer the humility of knowing how we may be wrong to the arrogance of believed certainty. The scientific motivation for analyzing data is to increase knowledge, as we are talking about p-value. A classical statistical uncertainty measure is the p-value. If it is small, one has found something. Then the result is called significant and published in scientific journals. Lately, some panic is going on as it turned out that many findings are not irreplicable. The statistical uncertainty measure seems not to be reliable. The p-value is cheating, they said. However, there is no reason for surprise as there is no outlet for publishing insignificant results. Maybe editors should invite authors to write about their journey along the path of insignificant results that led to the significant one. There is moreover also no reason for panic. False positives are part of the process of gaining knowledge and insight. The significant findings are subjected to further studies and sense has to be made out of it. Thus, statistics plays its role in understanding algorithms, the value of their outcomes, and consequent decisions for new research directions. Also, there is a small and growing literature seeking to address the lack of uncertainty quantification in high-dimensional data. For example, focused on penalized optimization methods such as lasso. Lasso, proposed by Tibshiani in 1996, is an acronym for Least Absolute Shrinkage and Selection Operator. Among the main reasons why it has become very popular for high-dimensional estimation problems are its statistical accuracy for prediction and variable selection coupled with its computational feasibility. Furthermore, since the lasso is a penalized likelihood approach, the method is rather general and can be used in a broad variety of models. In order to deal with the large dimensionality, modern statistical methods focus on regularization approaches that impose constraints on the model parameters so that they can still be reliably estimated even when the number of parameters is large. However, the frequent literature on uncertainty quantification in high-dimensional settings is still quite young and limited in scope. These are two important sources that a statistician must read while working with big data at the early stage of his or her career. To handle the challenges of big data, we need new statistical thinking and computational methods. For example, many traditional methods that perform well for moderate sample size do not scale to massive data, as we said before. Similarly, many statistical methods that perform well for dimensional data are facing significant challenges in analyzing high-dimensional data. To design effective statistical procedures for exploring and predicting big data, we need to address big data problems such as heterogeneity, noise accumulation, spurious correlation, and incidental endogeneity, in addition to balancing statistical accuracy and computational efficiency. We pointed these things before. In terms of computational efficiency, big data motivate the development of new computational infrastructure and data storage methods. Optimization is often a tool, not a goal, to big data analysis. Such a paradigm change has led to a significant process on development of fast algorithms that are scalable to massive data with high dimensionality. This forges cross-fertilization among different fields, including statistics, optimization, and applied mathematics, or maybe parallel computing methods and approximate algorithms that are scalable to large sample sizes. The ideas behind the problems we have to face as statisticians are mainly two. Firstly, the fact that at present most activities generate data that contains information. The second one is well summarized in John Walker 2014. Data-driven decisions are better decisions. It is as simple as that. Using big data enables managers to decide on the basis of evidence rather than intuition. The opportunities offered by big data are undeniable, but there is still a debate about the scope and usefulness of this. The opinions of the most fervent followers speak of the end of the theory and the models, and in articles like Controversial, the End of Theory, for example, as Anderson in 2008, they argue that with enough data, the numbers speak for themselves. On the other hand, there have been more critical voices that question whether the optimism and the faith that is being put into the big data are really justified. In this time, Tim Harvard wonders if we are making a mistake in other proactive article. In this paper, we will review some of the big data aspects that can generate doubts from the point of view of a statistician trying to describe if the data are sufficiently by themselves or it is necessary to give them a sense. First, it's convenient to be more specific. Although there is no single definition, there seems to be a certain consensus that big data encompasses the study of problems so big that conventional tools and models cannot handle them, either because they are not adequate or because they require too much time. In any case, whatever the definition we choose or where we put the emphasis, what is clear is that current technology generates huge amounts of data. So we had to be able to extract the best information from them and use it to make the best decisions. From the classical statistics point of view, the massive amount of data could be a blessing as we should be nearer to the real populations and the asymptotic convergence of the models. However, in practice, it looks more like a curse. Big sample sizes entail storage and processing problems, and huge efforts must be done in terms of improving computational performance and developing new tools in order to handle such volume of data. But the real challenge for statisticians is to deal with the heterogeneity inherent to big data, which appears in different forms. Populations are no longer homogeneous or normal, consisting of different groups and communities, but makes valid most classical statistical approach based on convergence and central limit theorems. But heterogeneity also appears in the variety of complexity of the data managed in the areas where this kind of problems appear, such as medicine or business. Therefore, the data at hand are far from standard random vectors. On the contrary, data can be completely unstructured, coming from surveys, call records, web activities, social networks, and so on. All of this opens the door to a wide variety of problems, including a proper information encoding and combination of different types of data structure. Moreover, big data tends to include the usual problems of high dimensionality. So we are in front of a double course in both the number of features and observations. Some say that this is the end of statistics. On contrary, I believe this is one of the most exciting challenges that statistics has ever met. That is, developing efficient tools to analyze extremely complex data such as curves, networks, trees, images, text, and many more. There is evidence of a need for rethinking statistical thinking. Statistics needs indeed to stop, research, and look at its history to go over parametric and asymptotic inference. Take into consideration the huge but small corpus of literature in the field non-parametric statistics, and starting from there, rediscover and embrace one of its original missions, that is aiming indeed at developing both general and mathematically sound inferential tools. In the past, data was necessarily small and statisticians worked to extract the most value from a little information. Instruction in statistics was centered around these methods for small data. Sometimes a virtue was made out of manual computation on paper or with a pocket calculator to incorporate a deeper understanding of the methodology. Even as computing became cheaper and faster, statistical instructions stuck to small data sets with a preference for those that could reasonably be printed in a textbook. Statistics has never been more relevant and challenged from the discussions around the reproducibility of science to the changing nature of a sample and sampling, to technical challenges about the computational limitations of some models, and to the massiveness of data. Variation has not suddenly disappeared in the floods of data. Our goals of explanation and prediction have not suddenly changed, and our desire to capture our uncertainty and communicate it in a way that is meaningful is even more important. A student who plans a career in analyzing data needs to know both the small data world of statistics and big data, the world of computer science. These two worlds overlap substantially, and yet it is often difficult to become skilled in both. There is a rapid increase in master programs in data science, which drove a large number of students. A large part of the instruction focuses on acquisition, cleaning, manipulation, and storage of big data sets. This is valuable knowledge, but there is a danger in that small data sets often require only trivial curation. To the data scientists, such as small data sets will appear of little interest. Machine learning often performs poorly on small data sets. A student who focuses on big data skills will have serious weaknesses. As we statisticians become main players on the central scientific stage, it's essential for us to hold a very high bar for ourselves, just as great scientists always do. Besides specific circula in data science, it is remarkable to note that data science is being offered at undergraduate level and transversal to all majors. An example is offered by Berkeley University Foundation of Data Science, that is a course originally offered by the Departments of Statistics and of Computer Science, is now offered by the Data Science Division, created in December 2016 with a focus on undergraduate education. The course was collaboratively taught by two professors from statistics and computer science and attended in 2016 by approximately 500 students from all disciplines. An interesting evolution of this course edition is available. A similar trend is now occurring at Harvard, where data science, introduction to data science was opened last year to all the disciplines and was attended by about 300 students. Another important aspect of the current shift in data science has to do with pragmatics. Data science is applied to solving concrete problems as clearly described by the syllabus of Berkeley course Foundation of Data Science. Many graduate data science programs were started recently. Among them, the Harvard Faculty of Arts and Science launched a new Master of Science degree in data science under the joint academic leadership of computer science and statistics faculties. The program is administered through the Institute for Applied Computational Science of the School of Engineering and Applied Sciences. The program is described as follows. Data science lies at the intersection of statistical methodology, computational science, and a wide range of application domains. The program will offer strong preparation in statistical modeling, machine learning, optimization, management, and analysis of massive data sets and data acquisition. The program will also focus on topics such as reproducible data analysis, collaborative problem solving, visualization and communication, and security and ethical issues that arise in data science. So after all this, when we came back to 3Ws, again we say that we have been at every stage of analyzing data and we will continue to be there. These are the sentences I use for this presentation. And thank you very much for your interest.